Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning. Okay, so today we will start with a new chapter for Principles of Electrical and Electronics, PKG 1123. So today we will cover on chapter 4. So chapter 4 is focusing on diode. So this diode is actually an electronics equipment. Okay, so chapter 4 will cover solely for the diode, and we will finish chapter 4. We will cover chapter 4 in 2 weeks, meaning this week and also next week. Okay, so for this week we will cover on the diode structure, diode characteristics, and also the Zener diode. And then next week we will cover on the diode applications. Okay. Okay, so these are the topics that we will cover in chapter 4. So we divide it into two parts. So the first part is the semiconductor diodes, which cover on the introduction, operation characteristics. Okay, so this one we will cover in this week syllabus. For this one, the diode application we will cover in next week lecture. Okay. And these are the learning outcomes for chapter 4. So in total, we have 7 learning outcomes. Okay, you can read it one by one. So basically for this week, we will cover up until learning outcomes number 3. Okay, so this week we'll cover describe the basic operation and characteristics of a diode in forward bias and reverse bias region. Second one, explain the IV curve of the diode in forward bias and reverse bias region. And lastly, we will cover on the explain, you should be able to explain the operation and characteristics of a Zener diode, Schottky diode, and also photodiode. Okay. So without wasting time, let's start with the start our lecture. Okay, for the first part. So if you still remember in last week lecture, you have learned on the last week lecture is chapter 3, which is introduction to semiconductors. Okay, and you also have learned about the N-type semiconductor and also P-type semiconductor. Okay, so this is actually a continuity from the chapter 3. Okay, the last part in chapter 3. So if you already forgot, I hope that you can refer back to your chapter 3 lecture. Okay, what is N-type, what is P-type semiconductor? Okay, so from the previous chapter, there are two types of semiconductor. We have N-type, we have P-type. So the N-type semiconductor, it has a majority carrier of electrons. While the P-type semiconductor, the majority carrier is holes. Okay, so N is negative, P is positive. So when you combine these two material, the N-type and also this P-type material, okay, you can actually construct a solid state device, which we call as the diode. Okay, so diode is made of these two materials, N-type materials and also P-type semiconductor materials. Okay, so you combine these two materials, you will construct a diode. Okay, so this is the figure of a diode. Okay. So usually you have a line over here. So the line over here indicates that this is the negative part. Okay, negative polarity. This is negative, this is positive. Okay. So first, what is diode? Diode is an electronic equipment which has two terminals or electrodes, and it actually acts like a switch. Okay, so I'm sure that you guys already know what is switch, what is the function of switch on and off. Okay, so later we will go into details about how this diode works. Okay, next is the symbol, diode symbol. So these are the schematic symbol of a diode. So you look at here, this you can see that this diode is actually a combination of the N material and also P-type material. Okay, so when you combine both, you get a diode. Okay, so the N type material is connected, is the cathode. This one is the anode. This is positive, this is negative. Okay, so when you draw a circuit, this is the symbol that we use. Okay, and remember, diode has a polarity. Okay, so this part, the triangle here, this is positive, and the line here is a negative. Okay, and this is the symbol of a diode. Okay, similar to this one. This is a diode. Remember that I said previously that for a diode you have a line over here. So this line is to indicate that this is a negative polarity. This is negative, this is positive. So same for this one. If you have see that you have a line over here, meaning that this is negative, this is positive. This is cathode, this is anode. Okay. So what is the function of diode? It is used to allow current to flow in a circuit in one direction and blocking the current from opposite direction. So diode can only allow current to flow in one direction only. It cannot allow current to flow in two directions. Okay. So how is diode is formed? Okay. Actually is the same as what we have learned in chapter 3 about the doping process and so on. Okay. So how diode is actually formed? So there are several steps. We have 1, 2, 3, and 4. Okay, 4 steps. So you need to remember these 4 steps how a diode is formed. Okay. So the first step here is the doping process. It's what we call as doping process. You have learned on doping process in chapter 3. Okay. So doping process is the process of doping more than one semiconductor materials. Okay, for example, silicon, germanium, etc. Okay, so you dope these semiconductor materials to create P-type and also N-type semiconductor materials. Okay, so how you dope and you create the P-type and N-type semiconductor materials, please refer back to chapter 3 that we already discussed previously. Okay, so I already explained in details about how we create a P-type and N-type material using a doping process. Okay, so the first step is the doping process. So when you dope this more than one materials, you will get the P-type materials and also N-type semiconductor materials. Okay, so after the doping process is the PN junction. So PN junction is if PN junction is created when the P-type and N-type material are joined in a close contact. So if you look at here, okay, so this is the second step, PN junction. So the PN junction is the junction in the middle. Okay, so the PN junction is created when both the P-type material and the N-type material are joined in close contact. Okay, so it is joined in close contact and it will create a PN junction in the middle. Okay, so this is the PN junction. Okay, the next steps, the third, is the diffusion process. Okay? Diffusion process. So what is diffusion process? It is when some of the free electrons in the N region over here, some of the free electrons in the N region diffuse across the junctions and combine with the host to form negative ions and leave behind positive ions in the N regions. Okay, and also vice versa. So a space charges builds up and creating a depletion region, which preventing further diffusion of carriers across the junction. Okay, so this diffusion process will actually create what we call as a depletion layer due to the free electrons in n region diffuse across the junction and so on. Okay, so you will have the depletion region in the middle. And lastly, the diode is formed. So basically, this is actually the summary of all the 3 steps that I explained to you before. The diode is formed once the p-type and n-type material are placed in close contact. Okay, p-type, n-type are placed in close contact, and this will form a depletion region in the middle, which has a potential value. So remember, this is the depletion region, and this depletion region has a potential value. Okay, potential value. Remember what is potential value? Is actually similar to voltage. Okay, so this potential is known as the potential barrier, and it depends on the material of semiconductor. Okay, so if you use silicon, then the potential barrier value will be different than of a germanium. Okay. Next is we have the diode biasing method. So the term bias actually refers to the application of an external voltage across 2 terminals of the device to extract response or establish certain operating conditions for an electronic device. Okay, so there are 2 types of bias. We have the first one, we have the forward bias. The second one, we have a reverse bias. Okay, so what is the difference between forward bias and also the reverse bias? So first, let's look at this one is with no bias, no applied bias, meaning that the VD, the voltage, is 0, no bias. It's not the forward bias, it's not the reverse bias. Okay, so no applied bias meaning no electrical bias is applied. So you can see that you have, this is the P materials, this is the N-type material. So in between you will have the depletion region. So this is the basic concept of a diode that we already explained before. Okay, so if you don't, no VD or no bias is applied, so you have something like this. You have the P-type materials and N-type are combined together, and you will have a depletion region in the middle. Okay. So no external, no applied bias, VD equals to 0 actually means that no external voltage is applied. So meaning that there is no voltage. We don't put external voltage. Okay, so this is the positive, this is negative part of the diode. Okay, so no applied bias, VD equals to 0, meaning that we don't connect it to with the external volt. Okay, no external volt is applied. Okay, so you will have something like this. This is basic lah. You have P-type, N-type, and you have a depletion region. But what happens if we connect the circuit, connect the diode with an external voltage? Okay, so we look at here. Now this is the diode. We have the P region and also the N region. And now you look at here. Now we connect it with the external voltage. Now we have a voltage over here, the positive is connected to the P region, negative is connected to the N region. Okay, so this we call as the forward bias, where VD is bigger than 0 volt. Okay, so this forward bias, or we also call it as the on condition. Okay, remember I said to you that the function of a diode is similar, act like a switch. So meaning it has a on condition and also off condition. So this forward bias condition is what we also call it as a on condition. So this forward bias is established by applying a positive potential. Look at here. We apply positive potential to the P type and negative potential to the N type. Okay, so when you apply this positive to P type, negative to N type, the current will flow. Okay, currents will flow through the PN junction. Remember the PN junction in the middle. Okay, so the bias voltage must be greater than the barrier potential. Remember, in the middle we have the PN junction. Okay, PN junction or depletion region. So it has its own barrier potential, and this bias voltage must be greater than the barrier potential. So what happens in forward bias condition is, you know that as the same charges repel, okay, like the characteristic of a magnet. So you have same charges, it will repel, different charges it will attract. Okay, so as the same charges repel, negative and positive side of the bias voltage source force the electrons in the N-type and holes in the P-type material to recombine with the ions near the boundary. Okay, and the recombination will actually reduce the depletion region width. Okay. Okay, so in the forward bias, it will actually reduce the depletion region. Okay, this depletion region in the middle, it will reduce. Okay, so if I draw, this is the P region, this is the P, this is the N region, and then when there is no bias, okay, you still have the depletion region. Okay, this is no bias. For a forward bias, you have something like this. Now the depletion region, this is the P-type, this is N-type, depletion region here is now reduced. The width of the depletion region is reduced in forward bias. So this is the difference between no bias with the forward bias. Okay. So let me summarize what happens in the forward bias. So forward bias, the VT is bigger than 0. Okay, so when the VD is high, the depletion region width will reduce and the current will increase. Okay, the current that can flows is increased. Okay, so this is what happens in the forward bias condition. Okay, so when the depletion region is reduced, heavy majority flow across the junction due to a reduced barrier at the junction and strong attraction for the positive potential applied to the p-type material. So as the applied bias increase in magnitude, the depletion region will continue to decrease in width until a flood of electrons can pass through the junction, resulting in exponential rise in current. So this is what I explained before. Okay. For forward bias, so when the VD is increased, okay, the depletion region width is reduced. Okay, so when the depletion region is reduced, meaning that more electrons can cross the depletion region. Okay, so this will result in rise in current. Okay, so when the depletion region is small, more electrons can um, actually the word is cross. Okay, more electrons can cross the depletion region. Okay, and the current will increase. Okay. So once the applied voltage exceeds a knee voltage, okay, later I will explain what is a knee voltage, the current exponentially increase. Okay, so this is what happens in a forward bias condition. Okay, so the knee voltage refers to the potential barrier of a p-n junction depending on material of semiconductor. Okay, so different materials, you have different potential barrier or different knee voltage. Okay, so for example, for silicon, the knee voltage or the potential barrier voltage is 0.7, for germanium is 0.3. For this is gallium arsenide, if I'm not mistaken, it is 1.2 volt. Okay, so what is knee voltage? Knee voltage is this. This is the knee voltage or the potential barrier voltage. Okay. Okay, so this is the knee voltage VD. Okay, so later we will go into details on this VI characteristics. So this graph is what we call as the VI characteristics. Okay, so this is the forward bias condition when VD is more than 0 volt. Okay, so previously it already stated over here, as the applied bias increase in magnitude, the depletion region will continue to decrease in width until a flood of electrons can pass through the junction and will result in an exponential rise in current. So this is what it means by exponential rise in current. So when it reaches the knee voltage, then you can see that you have an exponential rise of current when it exceeds the knee voltage. So in the previous slide, it stated that for different materials, you have a different VD or different knee voltage or potential barrier voltage. Okay, so for example, uh, for a silicon, you can see that this is the VI characteristic for a silicon where you have an exponential rise at 0.7. At 0.7. For this one, is germanium. Okay, so this is the graph for the silicon where the knee voltage is 0.7. This one, this is the graph, VI graph for the germanium where the knee voltage is 0.3. Okay, so that one is forward bias. Now let's look at reverse bias. So reverse bias happens when VD is less than 0 volt. Okay, so in previous bias condition, it prevents current through the diode. Okay, meaning it's an off condition. So so this reverse bias condition happens when the negative polarity of the external voltage is connected to the P region, while the positive polarity of the external voltage is connected to the N region. Then we will have a reverse bias condition. Okay, so what happens? Similar to the forward bias. So as the electrons flow towards the positive side of the voltage source, additional positive ions are created and the holes in the p-type are attracted by the negative terminal away from the junction. Okay, and this will cause the widening of the depletion region. Okay, so when the depletion region width is widened, so majority of electrons cannot diffuse across the junction and recombine with the host. Thus, it will result in a small current. Okay, so since this current is very small, it can be neglected. Okay, so what happens in reverse bias? The summary is, so VD is less than 0, okay, small VD. So when the VD is small, what happens is that the depletion the depletion region with this one will increase. So look at here, the depletion region width is increased. So when the depletion region is increased, majority of the electrons cannot diffuse across the junction. Okay, when the depletion region is increased, meaning the potential barrier voltage here is increased. Thus, majority of the electrons cannot diffuse across the junction to go to the P region. Okay, so when this happens, the current will be reduced. The current will become small. And this current is very small, and thus you can neglect the current. Okay, meaning that we take into account that current I is equals to 0 because it is very, very small. Okay, so this is what happens in the reverse bias condition. Okay, so this is very important. You need to be able to explain the condition of a forward bias and also reverse bias of a diode. Okay, so this is the VI characteristic of a reverse bias. So you look at here, previously I already told you that in a reverse bias, the current is very, very small and you can neglect it. So that's why in the reverse bias region, this is the reverse bias region where this is VD 0. Yeah? This is 0 volt. So when VD less than 0 volt, the current is very, very small because it falls in the reverse bias condition. Okay. So this, the forward bias condition we call as the on condition. This is the off condition. Why it is the off condition? Because the current is very small, because it blocks the current. The current in the reverse bias condition is very, very small, and we approximate as 0. Okay? So this is what it means by diode acts like a switch. Okay, so in the forward region, forward bias condition, it acts as on. Reverse bias condition, it acts as a off switch. Okay, so other than the forward bias region and also reverse bias region, we have another region which we call as the breakdown region. So this is the third region, the breakdown region. Okay, so remember this figure, this is the VI characteristics. We call this graph as a VI characteristics. This is the voltage, this is current. Okay, so you know that this part is the forward bias, this is the reverse bias region, but this part, okay, we call as the breakdown region. Okay, so what is breakdown region? It is a part where the applied external voltage is too negative or very high in reverse bias. Okay, the external voltage is very high in reverse bias. So beyond this point, the current increase at very rapid rate. And this reverse bias potential that cause rapid change is called the breakdown potential. Okay, or we have the VBV over here, breakdown voltage. Okay, reverse breakdown voltage, VBR. We call as the reverse breakdown voltage. Okay, and this part over here we call as the Zener region. Okay, we also call it as a Zener region. So later we will look into Zener diode. Okay, Zener diode is a diode that can works in this Zener region or the breakdown region. Okay. Okay. So this one, this is the summary of the difference between forward and reverse bias. Okay. So this one is forward bias, this is reverse bias. Forward bias happens when the positive external voltage is applied to the P region and the negative polarity of the external voltage connected to the N region. Okay, so in forward bias, the depletion region over here will be reduced. Okay, the depletion region is narrow. So the bias must be greater than 0.3 volt for germanium or 0.7 volt for silicons. Okay, so the depletion region voltage depends on the material, this V barrier. So V barrier is depends on the materials. Okay, so if the material is germanium, then the V barrier is 0.3 volt. If the material is silicon, then the V barrier here is 0.7 volt. Okay, so you look at here, the depletion region of this forward bias is smaller compared to the reverse bias. So for the reverse bias, It happens when the negative polarity of the external voltage is connected to the P region and positive polarity is connected to the N region. Okay. So what happens? The depletion region width will increase. Okay, the depletion region will widen. And the bias must be less than the breakdown voltage, and the current flow is very small, thus it can be negligible in most cases. Okay, so this is the difference. This is the summary of what is forward bias and also reverse bias. Next, let's look at the IV characteristics. So IV characteristics is this graph, the graph that shows the current and the voltage of the diode. Okay. So if you look at this figure over here, you can see that this is the forward bias, okay, VD more than 0. This is the forward bias. This is the knee voltage for a silicon. For example, we use silicon. So the knee voltage here is 0.7. So as forward bias produces current through a diode, the current is called forward current. Okay, so from the graph with 0 volt across the diode, there is no forward current. The forward current increases gradually as you increase the forward bias voltage shown in from point A to point B. Okay, you can read it. You can read this by yourself. Okay, but what I want to show you is that for the forward bias, it depends on the material of the diode. So this is the silicon. So the knee voltage is 0.7. So this part we call as the forward bias. The voltage must exceed 0.7 volt in order so that it can operate in forward bias. Okay. This is reverse bias. So reverse bias region, remember this is the reverse bias region where the current is very small, and in most cases you can neglect the current, and this part is what we call as the breakdown region. Okay, so please read this statement by yourself. So this actually explain in detail about this graph. And this is the complete VI characteristic. So in the previous slide, I show you in the previous slide, this is the forward bias, this is reverse bias, and the breakdown region. So this is the complete VI characteristic curve for a diode. Okay, so you can see here, this is the forward bias, this is the reverse bias. Okay, this is the breakdown region. Okay, this is the VI characteristic for a silicon. Why? Because the knee voltage is 0.7. If the knee voltage is 0.3, then this graph actually shows the VI characteristics of a germanium. Okay, so you look at here, the difference between the VI characteristic. So this line over here, the first line, okay, this one. So this is the VI characteristic of a germanium. Okay, why? Because you can see that the knee voltage is 0.3. This one is the VI characteristics of the silicon. Okay, so the knee voltage is 0.7. And lastly, this is the gallium arsenide. The knee voltage is 1.2. Okay, so this is the VI characteristic for a gallium arsenide. Next, let's look at what is ideal diode and practical diode. What is the difference between ideal diode and also practical diode? So the ideal diode is a mechanical switch. Okay, in forward bias, it acts like a closed switch, which allows the current to flow. Okay, so meaning it is a on condition. For reverse bias, it acts like an open switch which blocks any current to flow through it. So this is the difference. So this is ideal diode in forward bias. This is forward bias. This is reverse bias. So for forward bias, this diode actually acts like a closed switch. Okay, this is closed switch. This is on. So when the switch is closed, the current can flow. But when the diode is in reverse bias, this diode will act like an open switch. Okay, like this. So the current cannot flow. Okay, and since the current is too small, we approximate it as 0. Okay, so this is the difference between forward ideal diode in forward bias and also reverse bias. Okay, so this is also explain the ideal diode in forward bias and also reverse bias in more detail than the previous slide. So you look at here in forward bias, the diode over here acts like a closed switch. Okay, acts like a closed switch. So actually over here you have the diode. Okay, over here. But in forward bias, it acts like a closed switch. Okay, that's why you have a straight line over here. Okay, so when you have a closed circuit like this, okay, so the resistance here is equals to 0 and the voltage is equals to 0. But in reverse bias condition, now the circuit, the diode acts like an open switch. So that's why the circuit here is open circuit. So when this circuit is open circuit, meaning that the current is 0, the current cannot flow, and thus the resistance is infinite, very high. So what is the difference between ideal diode and practical diode? So ideal diode, so this is the is a circuit of forward ideal diode forward bias and also reverse bias. So for ideal diode, forward bias positive connected to the positive, negative connected to the negative. Reverse bias negative connected to the positive, positive connected to the negative. Okay, so you look at here. For the reverse bias over here, the current is 0. So this is the VI characteristic of a ideal diode. Okay. Previously we draw it like this, right? You have the knee voltage. Okay, but over here we draw it as like this. Okay. So for ideal diode, this is 0 volt. Okay, meaning the forward bias region is at 0 volt. For the practical diode, remember for practical diode you have it depends on the material of the diode, whether it's silicon, germanium, gallium arsenide. For this one, for example, it uses a silicon material. So you have the knee voltage of 0.5 So instead of the forward bias here is start at 0, this one start at 0, this one is start at 0.7. It depends on the materials of the diode. So this is the difference between ideal diode and also practical diode. So for ideal diode or ideal equivalent circuit, the 0.7 level can be ignored in comparison to the applied voltage level. Thus, the circuit reduced to only ideal diode. Now let's look at Zener diode. So what is Zener diode? So remember this VI characteristics. You have forward bias, reverse bias, and you have the breakdown region. Okay, so normal diode can only work in forward bias and reverse bias. It cannot work under the breakdown region. Okay, so type of diode that is designed to work in the reverse breakdown region of its operating curve is the Zener diode. Zener diode is the diode that is designed to operate in the breakdown region. Normal diode cannot work in breakdown region. Okay, so two things happen when the reverse breakdown voltage is reached. The diode current will increase drastically. Okay, so the current here increased drastically, and the reverse voltage across the diode remains relatively constant. So these are the symbol for a Zener diode. Okay. Okay, so this is the symbol for a normal diode. This is the symbol for a Zener diode. So you can see the differences here. Okay, so when you have a diode like this, so you should know that this is actually a Zener diode. Okay, so the difference of a Zener diode with a normal diode is that when the voltage is bigger than the Vz, okay, so Vz is the the Zener diode voltage. Okay, so when V bigger than Vz, it is in on condition. On condition meaning that it is operating in breakdown region. Okay, so remember Zener diode is designed to operate in breakdown region. But if V is less than Vz, we call it as an off condition. So, and this is actually reverse bias, but it's not operating in the breakdown region. Okay. So Zener diode equivalence for on and off states. So this is on off for a Zener diode. Okay. When V more bigger than Vz, then this is on, meaning that it's operating in the breakdown region. But if V less than Vz, then it's a reverse bias, but it's not operating in the breakdown region. Okay, so there are several characteristics of Zener diode. We have Zener knee current, Zener test current, maximum Zener current, and also the nominal Zener current. Okay. So this is for example. This is an example. For example, you were given the specification sheet for a 10 volt 500 milliwatt 20% Zener diode. Okay, so you were given this information. This information is for the 10 volt 500 milliwatt 20% Zener diode. Okay, so from this specification, you can actually know that the Zener potential is expected to vary as a 10 volt plus minus 20%, which is from 8 volt to 12 volt. Okay, because the Zener voltage nominal is 10 volt. This is 10 volt. Since it is 10 20%, meaning is plus minus 20%. So 20% out of 10 volt, okay? So plus you will get 12 volt, minus you will get 8 volt. So meaning the Zener potential varies from 8 volt to 12 volt. And you can also calculate for the power PZ max. So the equation for the PZ max is 4I ZT multiplied with VZ. Okay, so if you want to calculate the power rating based on the table, based on the specification, using this formula, 4IZT multiplied with VZ. So 4 multiplied with the IZT is 12.5 milliamp. Okay, 12.5 milliamp, and the VZ is 10. Okay, so you will get the power is 500 milliwatt. Okay. So the Zener potential of the Zener diode is very sensitive to temperature, and this temperature coefficient can be used to find the change in Zener potential. So you have a formula over here to calculate the temperature coefficient. Okay. Where T1 is the new temperature, T0 is the room temperature, Vz is the nominal Zener potential at 25 degrees Celsius. So now let's do example 1. So example 1 stated, asks you to analyze the 10 volt Zener diode described by table below if the temperature is increased to 100 degrees Celsius. Okay, so you are given this value. The question asks you to analyze the 10 volt Zener diode described by table if the temperature is increased to 100 degrees Celsius. Okay, so by using this formula, you can calculate for the delta Vz, meaning the change in the Zener voltage. Okay, delta Vz is the change in the Zener voltage. Okay, so this is the formula. Just put in the values. You will get the change of Vz is 0.54 volt. So the new Zener potential is 10. So previously it is 10. So you add with this delta Vz, which is 0.54. So you will get the new Zener potential at 100 degrees Celsius as 10.54 volt. Okay, so when you use this formula, you look at here. This is the TC. This one, Vz 10. This is 100%. T1 is the new temperature, which is 100 degrees, minus T0. T0, if you look at here, T0 is the room temperature. We assume it as 25 degrees. Okay, why 25 degrees? Because Vz over here is the nominal Zener potential at 25 degrees. So we assume the room temperature is 25 degrees. Okay. So put in the values, you will get 0.5 volt. So the new Zener potential at 100 degrees is 10.54 volt. Okay. So actually what it means is that the Zener voltage nominal at 25 degrees is 10 volt. Okay. So what is Vz at 100 degrees? So Vz at 100 degrees is 10.54 volt. Okay. So note that from the table, the temperature coefficient is positive. Zener diode that has less than 5 volt of Zener potential has negative temperature coefficient, and this Zener voltage drops with an increasing of temperature. So now let's look at the application of Zener diode. So where this Zener diode actually used. So one of the application of Zener diode is act as a voltage regulator. Okay, so what is the function of voltage regulator? Is to maintain the voltage. Okay, so regulate means maintain. So the function of a voltage regulator is to maintain the voltage. So voltage regulator is designed to maintain a constant voltage despite predicted variations in load current or input voltage. Okay. You don't need to go into details on this. Okay, but you can read what is the function of a voltage regulator. Okay. So now let's look at this circuit. This is a voltage regulator with no load. Okay, over here there is no load, and you have a Zener diode over here. So assume V input, this is the V input, varies from V input minimum until V input maximum. Okay, so by using KVL, okay, you will get this KVL equation, V in minus IZ, IZ is the current, IZRS minus VZ equals to 0. And you can get IZ equals to VI minus VZ over RS. So if you want to calculate for the, because we assume that V in varies from V in min to V in max, so we change this. Okay, for IZ min is equals to V in min minus VZ over RS. For IZ max, this will become V in max minus VZ divided by RS. Okay, because this is the alternating current. So it varies from V in minimum to V in maximum. And you can also calculate for the power. So power dissipated is P equals to I, P equals to VI. So P equals to I multiply with V. So same as this one. P equals to IV. Now let's look at the voltage regulator with load. So now we have a voltage regulator with load. So this is what we call as the load resistor. Okay, so we have two conditions when the V in and RL is fixed, and also when you have fixed V in but a variable Rn. Okay, so first let's look at the first condition where V in and RL is fixed. So this is V in, this is RL. So step one, check check the state of the Zener diode. Okay, so when you have a circuit like this, what you need to do, remove the diode from the network. Okay, so this is your Zener diode. Remove the Zener diode from the network. So you have a circuit like this. And calculate the voltage across the resulting open circuit. So you need to calculate the voltage here, the V here. Okay, so the V here is in parallel with VL. So it's actually the same. The value is the same. V is equals to VL. Okay, so you can calculate for VL using a voltage divider. Still remember your voltage divider. So if you have a circuit like this, series circuit like this, you want to calculate for VL. So VL is equals to RL divided by R plus RL multiplied with V in. So you will get VL. And you know that VL is equals to V. Okay. So if V bigger than VZ, the Zener diode is on, which is it's operating in breakdown region. But if V is less than Vz, the diode is in off and is in reverse bias, but is not operating in the breakdown region. Next, step 2, substitute the appropriate equivalent circuit and solve for the desired unknowns. So first, substituting the Zener for the on situation. Okay, so you put this is when the Zener is operating on for the on situation. So by using KCL, you already know that VL equals to Vz, and Iz is over here. So Iz equals to IR minus IL. IL is equals to VL over RL, and IR is equals to this. And the power dissipated by the Zener diode is P equals to Iz Vz. Now let's do example 1. Example case 1. You are given this circuit. For the Zener diode network given, determine Vz, VR, Iz, and also Pz. And the second one, repeat part A with RL equals to 3 kilo ohm. So now RL is 1.2 kilo ohm. Okay, calculate for Vz, VR, Iz, and Pz. Okay, so from this circuit, you need to redraw. Take out the Zener diode, so you will have something like this, and you can determine the V. So V is equals to VL equals to RL over R plus RL multiplied with V in. You will get the V is equals to 8.73 volt. Okay, so the voltage is 8.73 volt, which is less than the Zener voltage Vz, which is equals to 10 volt. So the diode is in the off state. Okay, so since you already know that VL is equals to V equals to 8.73 volt, you can calculate for VR. So you will get VR equals to 7.27 volt. Iz, because this is open circuit, so Iz is equals to 0. So P equals to Vi. So since the I is 0, so automatically the power is 0 watt. Okay. So if the question asks you to draw the VI characteristics, okay, since the V here, since the V is 8.73, so you know that at this point the voltage is 8.73. Okay, before it's operated in the breakdown region. This one is the same, but you just change the circuit, just change the load resistor from 1.2 kilo ohm to 3 kilo ohm. So the same procedure, you can calculate for the V. So V, you will get equals to 12 volt. So since voltage equals to 12 volt is greater than the Vz, the diode is in the on state, meaning the diode is operating in the breakdown region. And the others is the same. Okay, so you can calculate for the IL, IR, Iz, and also you can calculate for the power. Okay, so if you have a question like this, so this is how you answer. Next is the second case is when you have a fixed V input and a variable RL. So to determine the minimum load resistance that will turn the Zener diode on, you need to calculate the value of RL that will result in the load voltage VL equals to Vz. Okay. So this is the same. VL equals to VZ equals to RL over R plus RL multiplied with V in. So solving for RL, you will get RL minimum equals to VZ over V in minus VZ multiplied with R. Okay. So any load with the value greater than RL will ensure that the Zener diode is operating in the on state. Okay. So any load resistance value that is greater than the RL, ensure that the Zener diode is in the on state. And the maximum IL is equals to this. Okay, so once the diode is in the on state, the voltage across R remains fixed at VR equals to V in minus VZ. So I will not go into details on this. Okay, you can, this is the derivation. Okay, I hope that you can read this by yourself, the derivation of the IR, IZ, and also RL max. Okay, so I want to go directly to the example because it's much easier for you to understand based on example. Okay, so let's do example for case 2. So you were given this circuit. The question asks you, for the network, determine the range of RL. Okay, for case 2, now you have a fixed V input, variable RL. Okay, so for the network, determine the range of RL and IL that will result in VL being maintained at 10 volt. Second one, determine the maximum wattage rating of the diode. So the first question, to determine the value of RL that will turn the Zener diode on. So this one already explained in the previous slide, already been derived. So just use the formula RL min equals to this. Put in the values, you will get 250 ohm. Okay. So the voltage across the resistor R is VR equals to V in minus VZ. And the magnitude of IR is equals to 40 milliamp. And IL min you can also calculate equals to IR minus IZM equals to 8 milliamp. So the derivation of this you can refer in this slide. Okay. Then you can calculate the maximum value of RL, which is RL max is equals to VZ over IL min, so equals to 1.25 kilo ohm. So like I explained before, the derivation is over here. So if you hard to understand, so please refer to this slide on the derivation. But in when you do example or when you have a questions like this, you don't need to derive, you can just directly use the formula. Okay, use the formula, put in the values and you will get the answer. Okay, so and the second one, determine the maximum wattage rating of the diode. Wattage rating meaning the power. Okay, power, remember the power, the unit is in watt. So when the question asks you determine the maximum wattage rating, meaning the question asks you to calculate for the power. Okay, so P max is equals to VI, you will get 320 milliwatt. Okay, so it is quite hard to understand at first. So I hope that you can do this again manually. Okay, by yourself, not by referring to this slide. Okay, I want you to try and do the example by yourself because it's kind of hard to actually understand. Okay, but if you already familiarized with the uh, structure of the questions for the diode, then it will be easier for you because you just use the formula. Okay, so next we also have other types of diode. We have, other than the Zener diode, we also have this Schottky diode and also the photodiode. So this one, you can read it by yourself. Okay, you don't need to focus on this one. Just focus on the slide, on the how. Just focus on the slide explaining on the basic operation of diode, the IV characteristic of the diode, and also Zener diode. For the Schottky diode and photodiode, you don't need to focus, but you can read it by yourself. Okay, so this one, you can just read it by yourself. And if you have any question, you can ask me later. Okay, so this is the end of our lecture for today. So we will continue chapter 4, part 2, the diode application next week. Okay, so if you have any questions, you can ask me. You can ask me through. You can ask me privately or in the Telegram group. Okay, so thank you very much.